Volcanic eruptions unleash the fire and fury of our planet. We fear them, but often cannot predict them. We marvel at their primal beauty, their immense destructive power, their ability to reshape landscapes and change lives forever. Volcanoes remind us that we live on a living, dynamic planet, always changing, always creating and destroying. The Earth surely had to be the only place in the solar system where volcanoes could exist, the only world so dynamic and energetic that it could breathe fire. But now we know that view is untrue. There are many places in the solar system which have volcanoes. On some of these worlds, the volcanoes do not spit fire, but ice. A moon of Jupiter rages with more than 400 active volcanoes, perpetually erupting. There are long extinct gigantic volcanoes on Mars, one as big as the British Isles. And beyond, in the dark outer depths of the solar system, volcanoes stir. It's only in the last 50 years that we have realized that Earth is not alone in its volcanism, that right across the solar system we see past and present volcanoes unleashing their incredible power. This video is about them. But to provide a benchmark, if you like, for our tour of the solar system's volcanoes, we're going to start right here on Earth, home to a huge variety of volcanic activity. Volcanic eruptions on Earth can take many different forms, each with its own unique characteristics. What are the most common forms? Plinian eruptions produce towering columns of ash and gas that can reach high into the stratosphere. A famous example of a Plinian eruption is the AD 79 eruption of Mount Vesuvius, which buried the Roman cities of Pompeii and Herculaneum under ash and volcanic debris. Another example is the catastrophic 1883 eruption of Krakatoa. Phreatic eruptions are steam-driven explosions that occur when magma suddenly and violently interacts with groundwater or surface water, creating huge amounts of steam. In 2019, 22 tourists lost their lives in a phreatic eruption on New Zealand's White Island, shown here. Effusive eruptions are gentler, with lava flows that build shield volcanoes over time. Hawaii and Iceland are examples of islands built solely by effusive volcanic eruptions. Named after the constantly erupting Italian volcano off the island of Sicily, Strombolian eruptions feature moderate explosions and lava fountains, often from small steep-sided volcanoes. Examples include Mount Etna in Sicily and Mount Erebus in Antarctica. Both regularly erupt in Strombolian eruptions. Let's move away from the Earth now to the Moon. Its surface is dominated by dark plains called mare, which consist of basalts formed 3 to 4 billion years ago through extensive volcanic activity. In addition to the mare basalts, the Apollo missions also discovered orange and green volcanic glass beads, remnants of the Moon's fiery past. However, the Moon's volcanic activity has been extinct for over 1 billion years, indicating a significant cooling and reduction in internal heat over time. These features provide important clues about the Moon's geological history and evolution, including its early period of intense volcanic and tectonic processes. Mercury's surface is dominated by ancient lava flows that cover around 40% of the planet. These smooth volcanic plains were formed by massive eruptions billions of years ago. Irregular depressions on the surface mark the sites where these volcanic eruptions occurred. Mercury's volcanic activity ceased around 3.5 billion years ago, and the planet has been geologically dormant since then. This makes Mercury a volcanic ghost, a planet with a volcanic past but no present-day activity. Venus is often referred to as Hell's Furnace due to its incredibly hostile environment, with surface temperatures reaching over 450 degrees Celsius and crushing atmospheric pressure. Mount Mons is the largest volcano on Venus, standing 8 kilometers tall. It's a massive shield volcano formed by highly fluid lava flows. Pancake domes are a unique type of volcanic feature found on Venus, created by the eruption of extremely viscous lava that spreads out into flat circular shapes. There's evidence that Venus has experienced volcanic eruptions within the past few decades, and indeed latest research says that there may be as many as 26 volcanoes on Venus active today. So what evidence do we have of current volcanic activity on Venus? Well, here are two radar images of Mat Mons taken by the Magellan orbiter in February and October 1991. In the February image, we see an almost circular volcanic vent. But by the time of the October image, the same vent has changed considerably in size and appearance, indicating an eruption has occurred. This is just one example of several similar instances where we can see changes to Venus landscape which are difficult to attribute to anything but effusive eruptions. Moving out to Mars, Olympus Mons is the largest volcano in the solar system, standing at an impressive 25 kilometers in height. That's over 3 times taller than Mount Everest. The base of Olympus Mons spans an enormous 600 kilometers, roughly the size of the entire British Isles. This colossal volcano and smaller volcanoes across Mars' Tharsis Bulge has been dormant for an estimated 100 million years. Olympus Mons is a truly staggering geological feature, showcasing the immense scale and power of volcanism on the planet Mars. Io is the solar system's most volcanically active moon, with over 400 constantly erupting volcanoes. One such eruption is shown here in time-lapse images taken by NASA's New Horizons spacecraft when it was en route to Pluto. Jupiter's immense gravity squeezes and flexes Io's interior, generating intense tidal heating that powers this volcanic activity. The volcanic eruptions on Io often spew plumes of sulphur-rich material up to 500 kilometers into space, forming umbrella-like formations as they spread out. We can classify these as a sort of Plinian eruption, although different from Plinian eruptions on Earth because of the low gravity. They are also different because of their sheer scale. Such eruptions on Earth might eject just a few cubic miles of material compared to the hundreds of cubic miles of ejecta from a typical Plinian eruption on Io. Io is constantly resurfacing itself from effusive eruptions, which we know because of the lack of craters on Io's surface. These are similar to the eruptions on Hawaii or Iceland, but on a vaster scale. The length of volcanic eruptions on Io is linked to the Moon's orbit around Jupiter. They typically last weeks or occasionally months. All of this makes Io a truly unique and fascinating world in our solar system. Europa is another of Jupiter's Galilean moons, and it has a fascinating hidden world beneath its icy surface. The ice shell on Europa is 15 to 25 kilometers thick, a frozen crust covering a vast subsurface ocean that is over 100 kilometers deep. This ocean is thought to contain more water than all of Earth's oceans put together. Europa is a prime candidate for potential extraterrestrial life. Cracks and ridges in the ice shell suggest cryovolcanism, water plumes erupting through the crust from the subsurface ocean. Jupiter's powerful gravity causes tidal flexing of Europa's ice shell, generating heat energy that may drive this geological activity. Between 2014 and 2016, the Hubble Space Telescope imaged what are believed to be plumes erupting from these cryovolcanoes, although this has yet to be confirmed. But we may be able to confirm it soon. 2 spacecraft are currently en route to Europa in order to perform extensive studies of the Moon. NASA's Europa Clipper arriving in 2030 and the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, arriving in 2031. Moving out to Saturn, Enceladus, one of Saturn's moons, is known for its dramatic geysers erupting from the South Pole. These geysers are fed by fractures or tiger stripes in the moon's icy surface, spewing water vapor and ice particles in another example of cryovolcanism in the outer solar system. Beneath the icy shell, Enceladus has a warm interior with, it is believed, a subsurface ocean like Europa's. On the floor of this ocean, we think there are hydrothermal vents, similar to the so-called black smokers found on Earth's ocean floor, for example at the mid-Atlantic ridge. The plumes from the geysers have been found to contain complex organic molecules, suggesting Enceladus may have the ingredients for life. Staying with the ringed planets, we now turn to Titan. Saturn's largest moon harbours one of the solar system's most intriguing mysteries. How does Titan maintain its dense nitrogen-rich atmosphere despite billions of years of atmospheric loss? Recent discoveries point to cryovolcanism, icy volcanoes erupting volatile compounds, as the key to understanding this enigmatic world's dynamic geology and potential for harbouring life. So what is the evidence for cryovolcanism on Titan? Firstly, NASA's Cassini spacecraft observed dramatic surface transformations in western Xanadu, an area of the Moon shown here in a radar map between its 2005 to 2006 flybys, revealing new dark features consistent with cryovolcanic eruptions of water, ammonia and methane. There's also the fact that Titan's atmosphere contains argon-40, a radioactive decay product from its rocky interior, providing compelling evidence of ongoing internal geological activity, releasing gases from deep within. And cryovolcanism offers the most plausible explanation for how Titan sustains its dense nitrogen-methane atmosphere despite low gravity and continuous methane depletion over geological timescales. The existence of cryovolcanism on Titan is important for understanding this dynamic world and its habitability potential. Titan's methane cycle mirrors Earth's water cycle, with liquid hydrocarbons flowing across the surface, pooling in vast lakes and evaporating into the thick atmosphere, a phenomenon unique in the solar system. Cryovolcanic activity could sustain this cycle by releasing fresh methane from a subsurface ocean, possibly enriched with salts and ammonia, creating chemical complexity that may support prebiotic chemistry. Understanding cryovolcanism is essential for NASA's Dragonfly mission arriving at Titan in 2034, which will explore the Moon's surface and subsurface ocean for clues about prebiotic chemistry and the potential for life. Titan stands as one of the most compelling destinations in the solar system to study exotic geology, organic chemistry, and the fundamental question of whether life can emerge in environments radically different from Earth. We now move out to Neptune. Its largest moon, Triton, is known for its remarkable geological features, including active cryovolcanoes discovered by Voyager 2 in 1989. These cryovolcanoes, also referred to as geysers, erupt volatile substances such as nitrogen, methane and possibly water-ammonia mixtures. Voyager 2 revealed vast plumes rising up to 8 kilometers above the surface, driven by internal heat or seasonal solar warming beneath Triton's translucent nitrogen ice crust. These eruptions deposit dark material across the icy plains, creating streaks that trace prevailing winds and reveal ongoing surface renewal. Triton's retrograde orbit and likely origin as a captured Kuiper Belt object make this activity particularly intriguing, suggesting that tidal interactions and residual heat play an important role. Cryovolcanism on Triton provides valuable insight into how icy bodies can remain active far from the Sun, and it strengthens the case that similar processes may occur on other distant moons, with implications for subsurface chemistry and long-term habitability. And so we come at last to Pluto, surely one of the most enigmatic, puzzling and strange worlds in the whole solar system. Before the flyby of New Horizons in 2015, we had no idea what this world looked like. It was expected to be frozen and lifeless, orbiting as it does on the edge of the Kuiper Belt, that dark, cold outer zone of our solar system. Instead, we found Pluto to be a dynamic, changing world with incredibly varied landscapes and geology. Glaciers on the move, mountains of pure water ice, jumbled rocky terrains, frozen plains, plus strong evidence of past cryovolcanism. New Horizons did not see any active cryovolcanoes, but we should remember that the spacecraft was only able to observe one hemisphere of Pluto as it flew by. The other was in darkness. So we've only really seen half of this amazing world, and it's not impossible there could have been active cryovolcanoes on the night side when New Horizons flew past. Pluto's suspected cryovolcanoes include Right Mons, shown here, a 90-mile wide and 2-mile high landform. Right Mons can reasonably be described as a cryovolcanic analogue of a shield volcano on the Earth, but not a shield volcano in the terrestrial sense. Right Mons is extremely broad, gently sloping and low in profile, with a central depression reminiscent of a caldera. These traits closely parallel shield volcano morphology, which on Earth is produced by low viscosity basaltic lava spreading laterally. On Pluto, however, the lava would be water-based ice mixed with volatiles such as ammonia, erupting at cryogenic temperatures. The physics, chemistry, and heat transport are fundamentally different. For this reason, scientists typically use phrases like shield-like cryovolcano rather than applying the term unqualified. Pluto is a world of mysteries. No further space missions are currently planned to return there to investigate those mysteries, so many of us will never see Pluto again in our lifetime. But New Horizons flyby emphasized something which has been a revelation during our exploration of the dark depths of the outer solar system. That worlds which logic dictated should be frozen and lifeless are not. They are dynamic, changing worlds with activity and energy. We have seen that there are volcanoes across the solar system as rich and varied as the worlds which birthed them. From the giant volcanoes on Mars to the Fountains of Enceladus to the violently erupting Geysers on Triton, we see volcanism right across the solar system. Some of it familiar, most of it not. But what are the engines driving all that volcanism? There are three main sources of heat which drive volcanism across the solar system. Firstly, the radioactive decay of elements like uranium, thorium, and potassium has been generating heat within planets and moons for billions of years. This internal heat source is a fundamental driver of geological activity and the evolution of planetary bodies. Secondly, tidal heating from the gravitational pull of giant planets like Jupiter and Saturn can also create significant internal friction and warmth in moons and smaller bodies, as we see on worlds such as Io and Enceladus. And lastly, even after a planet forms, the residual heat left over from its initial creation continues to radiate outwards over time. These three key heat sources, radioactive decay, tidal heating, and residual heat, are the engines that power the internal activity and dynamics of many worlds in our solar system. Well, we hope you've enjoyed this video about the volcanoes of the solar system. If you have, why not give it a like and leave a comment? Tell us which of the worlds we've discussed you find the most interesting. Also, support Space Oddities by subscribing to the channel and clicking the notification bell so you don't miss any of our videos. It only takes a second and is completely free. We have more than 600 videos on the channel dealing with all aspects of astronomy, astrophysics, cosmology and space exploration, which we hope you will enjoy browsing through. Thank you so much for watching.